Greetings, research panelists. My name is Gabriel Jogno.
I am Liana Sarvallon. And I am Alliyah Lucas.
And today we will be presenting to you our study entitled In Silico Designing and Simulation of CRISPR-Cas9 Base Editors for TCF7L2 Variants Associated with Type 2 Diabetes.
Type 2 diabetes mellitus affects over 400 million people globally, with rising prevalence, particularly among younger populations, as highlighted by the World Health Organization in 2022. Current treatments, including medications and insulin therapy, manage symptoms but come with limitations such as side effects, dosing risks, and persistent disparities in access. These approaches do not address the root genetic causes, leaving room for complications like hypoglycemia and ketoacidosis.
Research by Chowdhury et al. 2023 emphasizes the significant role of the rs7903.146, a single nucleotide variant in the TCF7L2 gene, which influences insulin secretion and beta cell function, disrupting natural bodily functions, which increases risk threefold of developing a type 2 diabetes. The CRISPR-Cas9 system, as explained by Ed.D in Mundimote 2021, is an advanced genome editing technology. It uses a guide RNA to direct the Cas9 enzyme to a specific DNA sequence, creating precise edits. By targeting disease-associated genes like rs7903.146, CRISPR-Cas9 offers the potential to address one of the root causes of type 2 diabetes mellitus. This project focuses on designing single guide RNAs, sgRNAs, tailored to this variant using the CRISPR tool.
Now let us proceed with the following problem statements. 1. What is the specificity score of the selected sgRNA as measured by A. MIT specificity score, or B. CFD specificity score? 2. What is the predicted efficiency of the selected sgRNA according to the following models? A. Lawrence 16, B. Moreno-Matios, or C. Lawrence rule set 3. 3. What are the predicted outcomes of strand break repair by the selected sgRNA in terms of A. Out-of-frame mutations and B. Lindell predictions? 4. How many potential off-target sites might be affected, allowing for the following mismatches? A. 0 mismatches, B. 1 mismatch, C. 2 mismatches, D. 3 mismatches, or E. 4 mismatches. Now let's go on with our following objectives. 1. To evaluate the ability of the selected sgRNAs to accurately target the intended genetic sequence utilizing different specificity scoring systems. 2. To assess the effectiveness of sgRNAs in achieving successful gene editing based on computational efficiency models. 3. To explore the types of genetic modifications resulting from strand break repair caused by the sgRNAs, including frame shift mutations and other predicted outcomes. 4. Determine the potential for the selected sgRNAs to unintentionally target similar sequences, considering varying levels of sequence mismatches. Now for the methodology. Sequence obtainment. The sequences for the TCF7L2 gene variant rs7903.146 were obtained from the National Center for Biotechnology Information, or NCBI database. These sequences were retrieved in FASTA format by searching the variant IDs rs7903.146 on NCBI, ensuring that all necessary metadata were included for accurate analysis. The sequences were downloaded to serve as the foundation for sgRNA design and subsequent analysis.
Designing and on-target and off-target scoring. The sgRNA design and scoring process was carried out using CRISPR. This tool's CRISPR design module was used to generate candidate sgRNAs based on the TCF7L2 target sequences. Adjusting the parameters, the species that will specifically be used is Homo sapiens GRCH38x38. The standard sgRNA parameters, which is 20 nucleotides long plus 3 nucleotide NGGPAM sequence were used. The sequences were uploaded to CRISPR, where sgRNA candidates were identified for the TCF7L2 variants.
CRISPR scoring system provides multiple metrics to determine efficiency, such as specificity, which means the ability to target only the intended site, predicted efficiency, which means the ability to bind successfully into the target gene to induce an effective double-strand break, possible outcomes such as out-of-frame mutations and Lindels, and possible off-target sites if the cuts are not precise, specifically Cas9 protein cutting on lookalike targets with 4, 3, 2, 1, and 0 differences. Data analysis. To come up with conclusions, each scores were compared to the scoring standards in each metric, in order to come up with optimal sgRNAs and eliminate others. Standard scores for each metrics were followed. Usually higher is better, but the sgRNAs with moderate efficiencies were sgRNAs that present metric scores above 50 in specificity, efficiency, and predicted outcomes. For mismatches, lower is better.
Given that guide RNA 1 demonstrates the best combination of specificity, efficiency, and low off-target risk, it should be prioritized for experimental validation and in vivo applications. Its strong Lindell score further suggests that it has a high likelihood of achieving successful gene knockouts, making it the most reliable candidate for CRISPR-Cas9 gene editing in this study. However, given that predicted efficiency presented, although optimal but slightly lower than other metrics, we must take note that there is a higher chance of inefficient binding than lower specificity and inability to induce frame shift mutation. Based on the result, it is most likely that the sgRNA can effectively operate CRISPR-Cas9 as a gene therapy for the genetic variant significant risk factor for type 2 diabetes. And that ends the presentation of our study. Thank you for watching and listening.